Greetings, sir, and everyone watching this video. I'm Vijeta, and today's presentation is all about derivations and equations regarding DC motors. And I'll be talking about three kinds of equations, which is EMF equation or EMF generated in the DC motor, and torque equation and speed control. So let us jump into the basics first to understand these three equations. So first basic topic is magnetic flux. What is magnetic flux? So magnetic flux is basically when you have a magnetic field and some field lines. So when the field lines are passed through a certain area in a magnetic field, you'll be getting a density of field lines at a particular area, which is known as the magnetic flux. So as you can see here, X represents the field lines going into the surface, and O represents the field lines coming out of the surface. So in this diagram, the field lines are going into the surface, and the area we took is of a square area, and there are four field lines going into the square area. So what if I want to reduce my magnetic flux, or I want to reduce the number of field lines going into a square area? What I'll do is either I can reduce the area of the square, which is given in the second case. And when I reduce the area of the square, automatically the number of field lines passing through the area will reduce. But in practical cases, I can't actually reduce the area of a certain square or a circle so easily, right? So what I can rather do is that I can rotate the particular area so that the number of field lines passing through the area gets reduced. So when it is like this, then the number of area lines going through it is a lot more. And when I keep rotating it like this, and when you see it in the front plane, and remember we're talking about only one plane, so in one dimension. So when I see it like this, the number of field lines passing through the area is lesser compared to the before one. So in this way, I can reduce the number of field lines and automatically reduce the flux, magnetic flux effect it is having on the coil. So this can be represented by phi, and magnetic flux, which is phi, the equation for it is given by B A cos theta. So B is the magnetic field, and A is the area. So theta is the angle at which the coil is rotated. So when the coil is straight, the theta is 0, and the cos 0 is 1. So the flux, magnetic flux is given by B into A. So as it keeps increasing, the cos theta keeps decreasing, and the magnetic flux keeps decreasing. So this is how we are going to calculate magnetic flux. And let us look at the second topic, which is Lorentz force. So we have already studied in 11th and 12th physics about electric fields and magnetic fields. And electric fields are caused due to charges and the force between the charges. And magnetic field is caused due to two poles of magnet and the force between the magnets, which in terms creates a grid lines like this. Basically lines like this. And the equations for magnetic field and electric field are given by Fe equals to QA, and Fm equals to Q into V into P. So these are the equations, and whenever you have an electromagnetic field, there is a net of these two equations. So that can be represented by F net equals to Fe plus Fm, and this you'll get this equation. So while calculating this Lorentz force, we'll come across important equations for our further derivations, which is Fm equals to QVB. So we are concentrating only on magnetic field. Why are we doing that? Because whenever we are doing we are considering a motor, it acts on the principle of magnetic field generation or magnetic field. So whenever uh, electric field is electricity passed through the coil, there are two poles, which is north and south, and the coil is placed through it, and it creates a magnetic field along this setup. So we are mainly concentrated on this. So we'll be considering that equation, and we'll be writing the equation terms to our convenience as the following. So the V in QVB is velocity, and Q is the charge. So we know the basic equations for velocity and charge. Velocity is given by distance by time. So L is the basically the length, and T is time, uh, and I is equals to Q by T. So substituting this in the QVB formula. So in QVB, V is equals to L by T, and Q is equals to I into T. We'll be getting this equation. So finally what we'll be getting is Fm equals to BIL. Right. So this is the equation we'll be getting, and we'll be using this equation in further cases. So now let us come to the first derivation, which is EMF. So what is EMF? EMF is electromotive force, and basically it is equivalent to voltage. So EMF of a DC motor, it depends on a lot of factors, such as the number of poles are taken, number of conductors, number of paths, parallel paths taken, and so on. So let's start with um, phi, which is flux, as we have seen before. So flux per pole. So what does this mean? So this is a DC motor, and there are, as you can see, there are four poles in this case. In real cases, there are more than four poles. So four poles, and there is flux at each pole. And the total flux is, in this case, is P into 5, because we'll be considering the number of poles also. And so we know that the motor rotates with a certain speed, which is represented by N in RPM, and uh, we know that RPM is basically the number of rotations per 1 minute. So it can be represented here. So N RPM, basically N number of rotations, is in 1 minute, which is 60 seconds. So what about one rotation? If we require the time for one rotation, we can write as one rotation requires 60 by N seconds. So that's what we took here, time of one revolution, or in this case, revolution. So 60 by N seconds. And yeah, so now coming to the actual definition of EMF in terms of a formula is EMF is equals to d phi by dt, which says that the change in flux through change in time. So substituting that, we get 5 Pn by 60. Right. So from this equation, we need to consider more factors such as conductors and parallel paths. So what are conductors and parallel paths? Let us look at a diagram of DC machine. So in this diagram, there is a terminal here, and there are windings all over this. And there's the middle part is called armature. Basically, these are called armature. And we can see that in this armature, there are these red dots, which are also called as conductors, and it is the on top of it is a commutator, and these red and green ones are the brushes. So yeah, so basically there are the conductors are arranged in such a way that they are parallel to each other, and these are the amount between the two conductors is known as the parallel paths. So the number of conductors, we are taking it as Z, and the number of parallel paths are taken as A. So let us go back to the equation. So Z by Z and A. So number of conductors Z and this is A. So number of conductors in one parallel path is given by Z by A. So this is something which is you need to remember. And now this Z by A is multiplied with the previous equation. So when we multiply the previous equation, we'll get the EMF which is actually generated in the whole DC motor. So EG is given by 5P and Z by 60A. This is a very important equation because it is referenced in a lot of further derivations. So yes, so this is the EMF generated. Now let us move on to the torque equation. So torque is basically the twisting moment of force about an axis. So torque is basically force into radius, as you can see. And as we have seen before, Lorentz force equation is F is equals to BIL. And we have seen that phi equals to BA cos theta. So B equals to phi by A cos theta. Assuming that, cos theta is like we are taking only on one surface. So cos theta would be 1 here. So B is equals to phi by A. And as cross-sectional area is a circle here, so A would be given by 2 pi. And because it is a cylinder, we need to even consider the length. So 2 pi RL. So this is the area and, the part at which the field lines flow through. So yeah, 2 pi RL and phi, and P is the number of poles as we have discussed before. And you have I and L. So solving this, what you'll get is that P phi I by 2 pi R you'll get. And substituting this in the torque equation, which is F into R. So P phi I by 2 pi R into R, where R gets cancelled. And this is the actual torque equation you'll get. So T is equals to 5pi by 2 pi. And we should not forget about considering the conductors and the parallel paths, as we have done in EMF equation. So Z by A is also multiplied to the given formula. So finally, we get this equation. TE equals to ZP by 2 pi A into phi into IA. So here we can see that, the number of conductors and um, number of parallel paths and the poles, etc. are constant for a single motor. The only thing which is changing is the current which is given to the motor and the flux which is generated by the motor, magnetic field. So by this, we can say that the ZP to pi A can be retained as a constant, which is Ka, and the other two terms are variable terms. So Ka is also known as armature constant, and phi into A are terms, variable terms. So from this, we can say that T torque is proportional to phi into Ia Te. So we can conclude from this equation is that torque is depending on the current and the flux. This is the conclusion you get from this equation. Now let us learn a bit more about the EMF equation, which we have learned before. So the generated EMF equation you can see on the right, phi P and Z by 60A. And we know the angular velocity. So whenever you are rotating anything or, there's a twist and turn moment, there's always an angular velocity. It is given as 2 pi n by 60. And from this, we can derive the value of n, which is 60 omega by 2 pi. And when we substitute the n in the generated EMF formula, we get the formula which is similar to the torque equation. So this is 5PWZ by 2 pi A is the torque equation. And in this, so Z, the Z is constant, P area, sorry, A 2 pi. So this whole thing is a constant. So this whole thing can be taken and it can be written as Ka phi omega. So from this we can say that the uh, generated EMF is proportional to omega into phi, and the torque is proportional to Ia into phi. From these two equations or from these two relationships, what we can write is that Eg by T torque E equals to omega phi by armature current into phi. So phi gets cancelled, and Eg into Ia equals to torque into angular velocity. And as we know that torque into angular velocity is equal to the mechanical power generated. So we can write as torque into angular velocity is equal to the power, which is also equal to E into Ia. So if you remember in terms of electrical circuits, the power is equal to V into I. So where V is the voltage and I is the current, but here E is the EMF and I is the armature current. So yeah, we'll get another equation which is basically power equals to Eg into Ia equals to T into double. And also we should note down that the units for torque is Newton meters, EMF is volts, and the speed is RPM. Now let us come to the final topic of today's presentation, which is speed equation of DC motor. So what is speed equation of DC motor? I mean, why do we need to control the speed? So a DC motor generally gives an output of a constant speed, and we don't want constant speed for every single usage. So whenever you take a fan and you don't want constant speed every time it is switched on, you need to change its speed depending on it's hot or cold. So because of that, we need to change the speed of a DC motor depending on the situation and how what are the basic phenomena which we can control so that the speed of the DC motor is controlled. Let us see. So Eg equals to 5P NZ by 60A and N equals to Eg 60A by 5P Z. So in this, there's a thing that we need to note that Eg is basically EB. So what is Eg and EB? Eg is basically EMF generated, but the speed of the motor depends on the EMF, it depends on the backward EMF. So what is backward EMF? Let us see a small explanation on that. So back EMF. So whenever a coil is placed between two poles and a supply is given to it, so which is Vs, there's a forward EMF of Vs through the coil, which results in the rotation of the coil, and depending on the RPM of the coil, there's either a voltage which is uh, which comes backwards from the coil, or there is so in this way when you have a very low speed, a very low backward voltage which you get from the coil. So that is why we can say that the voltage which comes backward is directly proportional to the EMF. Voltage which comes backward is directly proportional to the speed of the motor, speed of the motor, speed of the coil. So this is the basic terminology. And so that's why we will use EB instead of EG because they both are related. So EB 60A by 5 PZ. And finally, from this, we can conclude that RPM is proportional to EB, and also flux, because the rest of all are constants, right? So it is only dependent on EB and flux. So the more number of rotations you have, so, the less magnetic field, the less flux is produced, and the less number of rotations, more flux is produced by this equation. So yeah, this is the basis. These are the equations of. These are the derivations which we need to remember. And thank you for giving me this opportunity to present these topics today. Thank you, sir. Thank you, everyone, for watching this video.